Hello there, and welcome back. So we're going to continue our discussion with parametrics, mainly with uses of the derivative of a parametric. So the next example we're going to take a look, it says we want to find all the points of horizontal and vertical tangency to the given parametric equation. So notice it says points, and we might remember anytime we see points, we are going to need both x and y coordinates. So we want to find the horizontal and vertical tangency. So let's talk about the horizontal first. Now we know when we do the horizontal, we did this earlier this year when we worked with implicit derivatives, that anytime we are working on horizontal, we're only interested in the change in the y value. So we want to know where dy is 0 or dne. So we need to take the derivative of just the y coordinate. So it's just the same as we've been doing. So I need to find dy, but remember we're in a function of t now. So when we take that derivative, dy dt, it's going to equal 2t minus 3. And we set that equal to 0. And that gives us t equals 3/2. So at t equals, so basically it says that 1.5 seconds, our particle is going to be horizontal. So we want to find out where that occurs now, and that's the point for us, okay? So we're going to go ahead and find the point of horizontal tangency. So we need to find the x-coordinate there and the y-coordinate. So we want to find x of 3/2, and that's going to become, what's that, 9/4 plus 3/2. I don't know what that is. The y-coordinate at 3/2, that becomes 9/4 minus, be careful, that becomes 9/2 plus 5. Now, I typed these in my calculator earlier, and what you wind up with is the point x becomes 15/4, and the y-coordinate becomes 11/4. So we get the point 15/4 and 11/4. And there's our horizontal point of tangency. To get the vertical, we know this earlier from this year, we want the change in x to be 0, dx to be 0, or dne. So we want to find x prime of t, so we want to find dx dt, because again, we're in terms of t this time, and that becomes 2t plus 1. There's nowhere where that will be dne, so we just set that equal to 0, and of course t equals -1/2. To get the point, once again, we just plug it into our x part of our parametric equation, x of -1/2, and that's going to become, what's that, 1/4 plus 1/2, which is, oops, sorry, that should be -1/2. There we go. So 1/4 minus 1/2 becomes a -1/4, and then to plug that into the y coordinate, negative, we're going to get, again, 1/4 plus 3/2 plus 5, and that becomes 27/4 if you reduce it. So remember, we're plugging in a negative right there, and this, of course, so our point becomes -1/4 and 27/4. So what's really nice about parametrics is because it doesn't care if it's horizontal or vertical, it's going to find it for us no matter what, and that's the idea of getting our function in terms of an alternate variable, in this case t, our parameter. All right, number 4, we want to set up an integral expression to find arc length given by the parametric equation. Now I'm going to go ahead and give you the rule for now, and we'll go over that in just a few moments. So to find arc length, now we did something very similar to this earlier this year when we did length of a function, and it's very similar to it. Arc length, we're going to call that little s, is the integral from a to b, the square root of, now when we did with the function, with our, when we did the length of a function, or length of a curve, we did 1 plus f prime of x squared. Well, the idea is the same here, but remember, we're not just dealing with the function in terms of y, but we also got our function in terms of x. So what we say is it's going to be this, dx dt squared plus dy dt squared dt. So now this is how we find the length of a curve as a parametric. So we have to deal with the x-coordinate independently and the y-coordinate independently right there. So this is our formula. You want to make sure you know that. So if we want to do this, ready? Our arc length, S, would be the integral between t goes from 0 to 1, 0 to 1, and it's the square root of the derivative of x with respect to t, so that becomes 2t squared, plus the derivative of y, which becomes 12t squared dt. And if you want to go on, then we can take a look at how we actually get that length right down here. All right, so let's take a look here. How we actually get arc length. If you want to take a look at this, how we get arc length in terms of a parametric. The idea is the same. So if I have a function where I'm looking for this arc length right here, I want to find the length between A and B. I'm going to take a little tiny piece of it. And you might recall earlier that that makes a rectangle. So let's talk about that a triangle, a right triangle. So if we look at that right triangle, if we blow that right triangle up, I know that this is my change in x, and this is my change in y. And of course, the length right here is this length right here is the square root of delta x squared plus delta y squared. And that's just really little tiny little piece. But we have an infinite number of these little arcs, right? I mean, these little pieces of the arc right there. So to add them all up, if I want to get all of these lengths, I am going to integrate this. The square root of delta x squared plus delta y squared. And I would integrate all these little pieces right here. But you got to remember, and of course this, whoops, we'll not do that yet. We shouldn't take the integral just yet. It's really the summation of all of them right there. And that's going to give me all these little tiny little lengths right there. But you got to remember, we're going to let delta x and delta y go to 0. And that becomes dx and dy. Of course, that's from our derivative. So then when we integrate this one, we get dx squared plus dy squared. And of course, we're integrating with respect to t here because it's a parametric. So that's really dx dt, and this is dy dt squared. And we get our dt on the outside here. If you wonder where that dt came from, look at my old video on how we get the length of a function. Same idea. And we would integrate that from a to b. Now, so that's how we get arc length. Now, if we want to get for function, this is of course for parametric. If we want to get to a function, well, what are we integrating with respect to? We're integrating with respect to not t, but with respect to x. So this becomes dx over dx squared plus dy dx squared dx. And notice this just becomes 1. And that's our old function formula there. So for function notation, we use this equation, a to b, the square root of 1 plus f prime of x squared dx. For function. For parametric, we are integrating with respect to t, so we use dx dt. Anyways, hope you enjoyed the videos. I will see you all later. Have a good day. Bye-bye.